Alright, picking up with the second three variable system, or three equation system, section 4.2, we find ourselves a system of equations where one of the three equations are missing a variable, which really doesn't necessarily change much of our approach, as you'll see here. Still, I like to label, either way, I like to label my three equations, so that when we refer back to them, we know what we're talking about. Equation 1, 2, and 3. And just kind of a little note, we are missing a x variable in this third equation, which doesn't necessarily mean anything in particular. But because it is missing an x variable, I guess it is possibly something that we'd want to use in our first step. But with any system, though, what we really want to look for is, as the equations originally are given to us, could we add or subtract to cancel out a variable that's involved? Okay. Adding or subtract the x's aren't going to give us 0. Okay, adding would give us 12, subtracting would give us 8. None of our y coefficients match each other, so adding or subtracting isn't going to work. But down here looking at our z's, we do have a 2z in equation 2 and a negative 2z, minus 2z in equation 3. So because those are opposites of each other, but the same number, just opposites, we can use those to cancel the z term. So that's where we'd want to start. Okay. So we can call this step 1, which is just trying to cancel one of our variables. So we'll start with equation 2 and equation 3. They're good as is. So we have 2x plus 4y plus 2z equals 28. Equation 3 is just the 10y minus 2z equals 36. So those two, because we do have opposite signs, to cancel out the z terms, we'd want to add. Okay. Doing so will cancel the 2z and the minus 2z. And we're going to get a new equation, which we will call equation 4. We're adding a 2x plus, there aren't any x, there isn't an x term there, so that's going to stay a 2x. 4y plus a 10y is going to become a 14y. And then on the right hand side of the equation, 28 plus 36 is going to give us 64. Alright, so there's our new equation we created, equation 4. So following the process that we did on the last example, we now need something that is going to involve the equation we didn't involve in step 1. So in step 1 we didn't involve equation 1, we just involved equation 2 and 3. So we now need to involve equation 1 in whatever we do. So we can call this step 2. And how exactly can we involve equation 1? Well, again, we have this minus 2z here in equation 3. We need to cancel out the same z term that we canceled out in step 1. So we have to try to cancel out the z term again here. So we can make this minus 2z become a minus 14z and cancel out the z terms by multiplying this equation by 7. Okay. So again, in step 2, not only do you have to use the equation you didn't use in step 1, but you have to cancel that same variable. So since we canceled z in step 1, we have to cancel z again. So here we can go with equation 1 as it is originally given to us. 10x minus 8y plus 14z equals 36. Okay. Then equation 3, we want to multiply it by 7 to make that a minus 14. So it matches up with the z term here. So 7 times equation 3 is going to give us a 70y. 7 times minus 2z is going to give us a minus 14z. And then 7 times 36 is going to give you 252. Okay. So again, we have opposites, 14z and minus 14z. When we have opposite terms, we add in order to cancel those out, to eliminate the z's, the z terms. So adding these two equations will cancel, will eliminate our z terms. And then what's left we will call equation 5. 10x plus no x term is going to stay 10x. Negative 8 plus 70 is going to give us a positive 62y. And that's going to equal 36 plus the 252 gives us 288. Okay. So now we have equation 4 we made, only has two variables, x and y in it. Equation 5 we made, only has two variables, x and y. It has to be those same two variables, because now we can go to do just the regular elimination. So we can come over here and call this step 3. Remember, step 3 is just regular elimination. So we do have 2x plus 14y equals 64, and then 10x plus 62y equals 288. The easiest way to eliminate a variable now with these two, it would be to make our x terms match up. 2x we can multiply by 5 to make it become a 10x, and then we could subtract the equations. It'd be more difficult to deal with. What do we have to do with 14 and 62? 40, yeah, that'd be a little bit trickier. So let's take equation 4, multiply it by 5 to make this a 10x here, and then we can keep equation 5 as it is to keep the 10x term here. Okay, so we have 5 times equation 4. It's going to give us 10x. 5 times the 14y is going to give us 70y. 5 times the 64 will give us 320. And then just keep equation 5 as it is. 10x plus 62y equals 288. Okay. So here we can subtract. Because they're the exact same terms, we have to subtract to cancel the x term out. X terms do cancel. 70 minus 62 gives us 8y. 320 minus 288 gives us 32. And now we have an easy equation we can solve for y. Divide by 8. Divide by 8. We end up getting that y equals 4. So there's one variable. We can take that variable and plug it back into, we have some options really. We could plug it back into equation 3, and that will help us find y, and or we plug it in for y, that would help, we could then find z. Or we could plug it into equations 4 or equations 5, the ones that we made ourselves. I would suggest, just in case for some reason you messed up in creating equations 4 and 5, take this and plug it back into one of your original equations, if that will make sense. So because equation 3 only had the two variables, we can plug it back into equation 3 for y and find out what z is. Alright, so taking this up here, y equals 4, we're going to plug that into equation 3, which was 10y. So 10 times our y value, which was 4, minus 2z, we're going to find out what the z is, equals 36. We then want to solve this for z. So that gives us 40 here. Minus 2z equals 36. Subtract 40 from both sides. We get a negative 2z equals a negative 4. And then divide on both sides by negative 2, negative 2. And we get that z equals positive 2. So we have two of the three parts of our solution. We have our y, we have our z. So once again, we have to go back and use one of the equations that involve x, y, and z, plug in our y, plug in our z, and then use that to find what x is. So obviously we can't use equation 3, since equation 3 doesn't involve the x variable at all. We can use either equation 1 or equation 2. Equation 2 is smaller numbers, doesn't have any negatives. I probably would use equation 2. So let's do that. Bring it back over here, give us some room. Equation 2 was 2x plus 4 times our y coordinate, which was 4. Where are we at? Oh, plus 2 times our z coordinate, which was 2, equals 28. Slide this up now that we've plugged in. So now we can come through here and solve for x. We have 4 times 4 is 16. The 2 times 2 will give us 4. So we can go ahead and combine those. 2x plus 16 plus the 4 is going to give us 20 equals 28. Okay. Subtracting 20 from both sides would cancel out the 20 here, would leave us with 2x equals 8. And then dividing 2 from each side of the equation is going to give us x equals 4. Okay. So now we have all three parts of our solution. Again, we want to write this as an ordered triple. Our x coordinate was 4, y coordinate was also 4, z coordinate was 2. So we always write it in alphabetical order, x, y, and z. Alright, so that one wasn't as bad, I think, as the first one, but still probably longer than something you really want to be doing. Fortunately, there's not really any easy way around that. Flipping over to the last page of 4.2 notes, we have two kind of special case examples, which will fortunately be quicker. And if you kind of spot that they are special cases, then these will be quicker. So I'll show you here what to look for to try to spot if they are a special case. Okay. So at initial glance, this is going to look just like the other two systems we just solved. Okay, 3 equations, x, y, and z. The last system didn't have all 3 equations with 3 variables, but it ended up working the same. So this looks similar to the first example we did. However, what we want to do in a problem like this, or any system of equations, try to see if two of your equations could be, if one equation could be multiplied by something to turn into one of the other equations. Or even if it doesn't turn exactly into the other equation, if it turns into something close. So looking at our 3 equations here, equations 1, 2, and 3. Equation 1, well, comparing equation 1 to equation 2, if we try to make these two match up to each other, we would have to multiply this equation 2 by 2 to try to make the 2x's. If we did that, we'd end up getting a 6y, which wouldn't match the 4y. We'd end up with a negative 4z, which wouldn't match the 6z. So that doesn't work. But looking at equations 1 and 3 together, if we multiplied equation 3 by 2, that would become a 2x to match that. That would become a negative 4y, which would match that. That would become a 6z, which would match that. And that would equal 2, which doesn't match the 5, but the other 3 parts matched. So that kind of should, when you see that, that should throw up a flag to try to combine those two equations together. And this is probably then going to be a special case. So we'll take equation 1 as it is, 2x minus 4y plus 6z is 5. Okay. And then take equation 3 and multiply it by 2 to make it look almost like equation 1. So 2 times x will give us 2x, 2 times minus 2y will give us minus 4y, 2 times 3z will give us 6z, and 2 times 1 will give us 2. So what we have here is almost the same equation. They're almost the same equations, but they're not. But because the two x's match up exactly with each other, we would subtract to try to cancel things out. And the minus 4y match up, we would subtract to cancel those. 6z matches up with 6z. So in all three of those cases, we would have to subtract to cancel out. But what's going to happen on the left-hand side of this equation, if we have a 2x minus a 2x, those will cancel. We have the same minus 4y, so when we subtract, those actually will cancel. 6z and 6z, when we subtract those will cancel. And we end up with 0 then on the left-hand side. If everything cancels, we have nothing. Right-hand side, 5 minus 2, we get positive 3. So this is one of those situations, just like when we were doing a system of equations with two variables. If we get to a point where we have a clearly false statement, well then this is what we call an inconsistent system, and there's no solution. So this is much nicer, a lot quicker. We get to our answer. So no solution. Sometimes in my math lab you'll see them use that symbol again, the null set. Okay? So that's what you look for. Find a special case, and hopefully it'll be one of those special cases and it'll be a much quicker problem. We can try to do the same thing on the next example, even though at initial glance maybe doesn't look like anything special, but try to see if something will match up with another equation. So again, let's take a look at this as equation 1, equation 2, and equation 3. Okay. Well, hopefully by looking at this and trying to apply it the same way we did on the last problem, we can make equation 1 become equation 3. Multiplying 2x times 3 will give us 6x. If we multiply then everything else by 3, negative 3 times 3 will give us negative 9. 4 times 3 will give us 12. 8 times 3 will give us 24. We actually will turn this equation into exactly the other equation. So that's how we want to approach this problem. So take equation 1 and multiply everything in it by 3. So 3 times equation 1 is going to give us 6x minus 9y plus 12z equals 24. Keeping equation 3 as it is, we have the exact same thing. 6x minus 9y plus 12z equals 24. So it's not almost the same equation in this one, it is exactly the same equation. So when you have things that are exactly the same, in order to cancel them out, again, we'll be subtracting. So 6x minus 6x cancel. The same negative 9y, if we subtract negative 9y from it, those will cancel. 12z minus 12z will cancel. 24 minus 24 will cancel. We end up getting ourselves, even if you just look at it and see they're the same equation, if you remember what that means from the systems in two equations, we get a true statement, or even if you just catch that they're the exact same equation, that's enough to know that it's going to be a dependent system, and we have infinite solutions. Okay. So two special cases, much quicker if you spot it that they are special cases. We don't have to work through all the steps that are involved with the other systems of equations. That's it for 4.2.